Hello, everyone. Hope you've had a great day so far. I know it's kind of the later half of the day, but I'm sure we're going to make this quite enriching. So are you all ready for this? Yeah. Awesome. That's the spirit. My name is Pranav Nambiar. I'm a senior manager on AWS. I also have with me Philip Clegg, who is the CTO of MirrorWeb. Together, we're going to talk to you about search and building high-scale search architecture using Amazon Elasticsearch service. So we're going to do this section into two parts. First of all, I'll cover an introduction to search, give you a peek into the various capabilities that Elasticsearch offers. I want to talk about the benefits of using Amazon Elasticsearch service. And then Phil is going to come over and tell you about the MirrorWeb story, how they went about building some cool architecture for their search at really good scale. So with that, let's get started. Since the session is primarily about full-text search, I thought, why not start with the definition of full-text search? Wikipedia puts it as a collection of techniques to search through fields in a document or a collection of documents against a search criteria. So on that note, how many of you have used full-text search? Just show of hands. OK, pretty much all of you. Well, search is pretty much everywhere. Use full-text search when you use Google search. It analyzes your text, tries to give you search results based on relevance. You use full-text search when you search on Amazon. It gives you the list of products. It allows you to sort by relevance. It even gives you facets on the side by which you can drill deeper and refine your search. You even use full-text search when you search on social media. You search for tweets, search by hashtags, and so on. Search is pretty much everywhere. And that's why the search architecture becomes that much more critical. But for us to understand, how to actually build an architecture that can stand the test of times, we should get a better sense of where search stands today. So to understand that, how about we look quickly at the evolution of search? So if you go back in time, a few decades in time, your primary source of data was your database, your traditional relational database. At that time, if you had to do a search, it would be a select star from where, like, query. If you had to try out different permutation combinations of your search term, you have to add it to your, select class and, try out queries. So what it did was, it would return to you a fixed set of results that match exactly to your terms. It operated on a smaller data volume. But soon, the world evolved. You got a lot of different kinds of data. You got the web content, you got documents, you got emails. And all this gave birth to the initial generation of search engines. These search engines brought a sense of relevance to search. So now it is not just about getting all matches, it is about getting the best possible match. But that was not enough. As the world evolved, if you fast forward to the current day, we got all kinds of data. We got some web contents to weather content, products, catalogs, and whatnot. And the modern day search engines have also evolved. They've got much better mechanisms to rank your search, providing you better relevance. They're able to handle a lot more data volumes. They also offer you interesting search features like faceting, suggestions. And also they have better language processing capabilities. So for us to look at search architecture, let's for a second ignore all the technology elements here and just look at the trends that we are seeing over the years. First of all, this is a no-brainer. Search has pretty much become an integral part of almost every product or service that you're building. You're building a mobile app, you need search. You're building any kind of e-commerce service, you need search. Almost everywhere you're looking, you need search, either externally facing or maybe even internal for your own consumption. The other key trend is structured data is now giving way to unstructured or semi-structured data. Gone are the days where you had everything in a tabular, relational database format. Now you got different, more flexible formats. But that's not it. Data volume is increasing. Your performance requirements are increasing. Also, the need to analyze text in a smart way, in a language-aware way, is also increasing. So now, given that you're all part of the session, I'm sure you all agree with the first point. But now when you're building a search architecture, you need to make sure that it can cater to all the other points, because that's where the world is heading. So in response to all this, the several search engines available in the market today. Here, according to DB Engines, these are the top 5 search engines, of which we're going to look at the first one, Elasticsearch. Elasticsearch is one of the more popular search engines out there. It's open source, easy to onboard, can handle high performance and high scale really well because it's a distributed system. It also offers you a lot of extensibility mechanisms. It enables you to ingest data and process data very well and visualize them well. It's also quite capable. It can be used even for analytics and search. But now, the key part here is it is a distributed system, and so you still have to deal with managing one or more clusters of nodes, and then handling the patching, the maintenance, the availability, and so on. That's where Amazon Elasticsearch service comes in. So Amazon Elasticsearch service gives you a managed interface for Elasticsearch. So literally what it does is it takes away the hassle of managing your instances, setting up, deploying, and scaling, and all that. So essentially, if you were to look at it in terms of benefits, what it does is, first of all, it's fully compatible with Elasticsearch, so it's open source APIs. You can easily just migrate and replace Elasticsearch with Amazon Elasticsearch. Also, it's highly easy to use because it makes it very simple for you by taking away all the overhead of management. It's got a lot of options for you to select different instances, very easily scalable, highly available, and secure. And of course, it's also well integrated with AWS. So if your data is in AWS, it's much easier for you to bring it into Amazon Elasticsearch service and actually process it either for analytics or for search. Let me give you an example. Let me just walk you through with an example. So let's say you want to build a catalog for books. So what you do, you go to the Amazon Elasticsearch service. You just either use the console or the APIs. Just with a few clicks, you can set up your cluster. You can pick the kind of instances that you want, and that's it. Amazon Elasticsearch service does the rest. Now you can ingest data to it, set up your indices, and get going. Now the part here is that this is not a typical, direct match of strings. It's a best possible match. It gives you a sense of relevance. And I'll tell you how you can configure that, the multiple aspects that you can extend here. So for example, if you need to search for Elasticsearch guide, it would return to you the perfect match, Elasticsearch guide, completely matching. It could also return to you Elasticsearch getting started guide or becoming an Elasticsearch expert. These are also, results that could match, though they don't match exactly to your string. So that's kind of an example of how actually search can be smarter and much more applicable to your modern day, requirements. Now I'm sure you might all be wondering, okay, so how do you go about actually building the search architecture? So let's dive right in. So this is the simplest form of a search architecture. Essentially what you do is you ingest documents to the search engine, and then you make queries to the search engine to get results. Inside the search engine is where the magic happens. First of all, the search engine takes the documents that you offer, processes them, takes it through a process called analysis, and then extracts the key terms that it needs to actually index for you. Subsequently, when you do a query, it figures out what are the key terms in your query that it needs to actually search against, goes into the index and pulls out the necessary documents, sorts them based on relevance, and returns it to you. Now I know it's all easier said than done, so let's dive into each of these bit by bit. The 3 phases here: indexing, text analysis, and querying. Let's look at each of them one step deeper. To help with that, let me use a data set to help illustrate the concept. So the data set here that I'm using is the IMDb database. Consists of around 5,000 movies, and each document here captures the various fields within a movie. So for example, here, for the Iron Man movie, there are full text fields like title and plot. There are also non-text fields like ratings and release date and so on. So let's dive into the first stage of indexing. Indexing is common. Even in databases, we all have encountered the term indexing. Simply put, indexing is just the process of organizing your data for fast retrieval. Databases use data structures like B trees. Elasticsearch uses what we call inverted indices. I'll tell you about it. So you have your documents sent to Elasticsearch. They're pretty much a JSON document. Essentially, they are like name-value pairs. I'll show you an example shortly. And then what it does is it subjects it through a process called analysis. From the analysis, it's going to look at each of your text fields and extract the various terms that it needs to index. So for each of these terms, it's going to build a list of documents that match those terms. So in your typical database world, you have documents and then the terms that are there within it, or the columns and fields. Here it's inverted in the sense that it tracks the terms and then matches it to the documents. Because when you query, it can easily get to the documents fast. So for example, in the case of the Iron Man movie, I'm just ingesting one document, which is a JSON document of the Iron Man movie. I've got an index called movies. I've created a document ID 12345, and I'm writing this in. It's got multiple fields: title, plot, and so on. Some text fields, rank, release date, and so on. Non-text fields. And what Elasticsearch does is it takes in, processes this, analyzes this, and indexes it all underneath it without me having to know actually what all is happening. Now, the key part here is the analysis part. And let me just elaborate on that, because that's very critical to control how your search behaves. So analysis is the process of taking your text and extracting the key terms out of it to build your index. So essentially, you provide your input text to the analysis phase. It consists of different analyzers. You could chain those different analyzers together. It could be built-in analyzers or custom analyzers. And then you get the output terms that actually form your index. Let me illustrate this with specific examples. And I'll take the example of the Iron Man movie that we just saw. So essentially, what I'm doing is we'll analyze the plot field here, which is like a full text string here. And we'll see how analysis can actually work on it. So analysis generally has two phases. The first phase is called tokenization, and the second phase is called normalization. So first of all, in the first phase, you take the string and convert it into tokens. And in this case, I've actually taken the example of a white space tokenizer. This is an inbuilt tokenizer that Elasticsearch offers, and what it does is it just takes the text, converts it into the various tokens, or in this case, it'll be the various words in the string. Do note that it also tracks the offset of the word and the position of it in the doc, etc., so that it can actually retrieve it fast in case you're searching against it. Now, it's distributed into tokens, but when you search, you typically want it to be case insensitive. So let's normalize it. So let's add a filter called lowercase. So this is again a built-in one. You just specify lowercase, and voila, it transfers and translates your string into a lowercase string. And so all tokens are converted into lowercase. But now if you look at the plot string that you have there, there are many words in it that don't necessarily add much to relevance for search. For example, you have got an, is, the, and a few such stop words. So what we do is we subject it to a stop word filter. And here I've taken an example where I am specifying the stop words that I want removed from my text. So here I'm customizing it a bit. There are multiple ways you can do it. You can even specify a file which contains your stop words. You could even use certain stop word analyzers which actually do it all for you. But here I'm just showing you an example where you customize it. So essentially what Elasticsearch does is it's going to strip off all these stop words. But now that's not it. So for example, if we take the word wealthy in here, if I were to search by the term wealth, you still want it to match to the string, wealthy. If I maybe search by wealthier, you still want it to match to it. So in other words, you would like to actually normalize it into some native form. So that's the process called stemming, and I could add a stemming filter as well. So look at it the way I've chained all this. You have a lot of flexibility here in terms of how you chain it. I've added an algorithmic stemmer here called Lovins, and what it does is it translates most of the words into its root form, if it's not already in that form. So wealthy, for example, became wealth. So later on, if I search by wealthier or wealthiest, it's still going to be able to actually map it to this kind of a string because it always converts it into its root form. So with that, that's at a high level, different forms of analysis. Now let's say we have analyzed it, it's separated into terms, it's in its normalized form. Now let's go into querying. So when you actually start querying, you're actually specifying terms that you want to match against. So what Elasticsearch does is it first analyzes your query. So for example, you search by the term wealthy, it transfers that also into its normalized form, wealth, and then it looks for all documents that match those terms. So if you have multiple terms in your query, it's going to look for all documents that match both terms. Subsequently, it's going to rank these based on a scoring algorithm, and we'll talk about that shortly, and then subsequently return back to you the sorted result. Let's look at it with some examples. Let's say you want to search for Iron Man. Well, simple. You just say query title Iron Man. And I got, I tried this on the IMDb dataset, and I got 77 hits. You can look at the score column, which is kind of the scoring that Elasticsearch does. The first 3 results are scored higher because they're kind of the exact match, the 3 Iron Man movies. I also have, results like the Iron Lady because it matched at least one of the terms. Now you might say, hey, I don't want this. I actually wanted to have an exact match. Simple. You just say match the whole phrase Iron Man, and it only returns to you 3 hits, the 3 Iron Man movies. Now let's say, you want to actually have some more complex queries. Let's make it a bit more complicated. Let's say you want to match all Iron Man movies, and you want to return only those that are rated more than 7. So here's what you do. You say match title Iron Man, and you say rating greater than or equal to 7, and it returns to you 33 hits instead of the 77 hits that we just saw. Now here, all of them are rated higher than 7 or more. Now let's say you want to add some faceting to this. Let's say you want to actually split this into buckets based on rating. If you say, okay, I want one bucket to be rated between 7 and 8, and another bucket to be rated greater than 8. So here's how it will look. You specify your facets, then you're saying, okay, return to me those that match these different buckets and organize them. And it returns back and says the 27 movies between 7 and 8 are in ratings, and there are 6 movies higher than 8. In fact, I found this pretty interesting. What I did was, so essentially the 33 movies out of 77 that are rated more than 7 that matched Iron Man. So I was curious. I actually searched for different other terms. I searched for love, I searched for action, and so on. And I found that not many of those come even closer. Their success criteria with these ratings was much lower. Like even with love, it was like 20% of the results had higher than 7 ratings. So Iron Man seems to be a good formula, to have a successful movie at least. So in case, you're looking to build any movies, something to think about. But anyway, I guess you get the point. The different ways by which you can slice and dice this. There's a lot of capabilities that Elasticsearch offers. There's one other key point that I actually want to cover here. That's about scoring and ranking. So Elasticsearch by default does its own, scoring of your results. You already saw that in the table that I showed you, where it scored your results. The default algorithm actually has, 3 key aspects that it actually evaluates you based on. The first one is, of course, your term frequency, how frequently a term occurs. The second one is what we call inverse document frequency. Basically, if a term occurs too many times within a document, Elasticsearch feels, hey, maybe it's not as relevant. That document may not be as relevant to the search, and so it dings it slightly in the score. The next one is field length. So for example, if a term matches a field with smaller length, most likely it's more relevant. For example, if a term matches the subject of an email, it might be a better match than it matching just the body of the email, right? Because subjects are generally smaller in length. So it has some mechanisms to actually build some kind of scoring around it. But you have the flexibility to change this around. You have the flexibility to actually tweak it, to define either based on the values within a field. You can even have a scripting function to actually change it and define how the scoring needs to be calculated. Let me illustrate it with a small example. So I searched for the term James Bond, and I asked it to match against title and plot, and it returned to me results. And the first result was Casino Royale with a really good score, and that was the very first result. Well, makes sense. It's a James Bond movie. But I said, well, I actually want to give title a lot more weightage in the scoring mechanism. So I actually increased the weightage of title and tried the query again. And this time, the result that was on top was the movie Bond 24. And the score went up. It was like 32.63 because I bumped up the title score by a factor of 5. So overall, what it illustrates is you have a lot of mechanisms to actually fine-tune your search scoring system based on your requirements to actually get the desired behavior that will lend to a good customer experience. There's a lot more, even just from the scoring aspect, the many different scoring models as well, but in the interest of time, I'm not getting into all those. But overall, the key point here is the many aspects here that you can actually fine-tune as you build the search architecture to actually provide you the right kind of experience for the customer. So all in all, to quickly summarize this, Elasticsearch is a great technology for full text search. Offers you a number of capabilities. We saw faceting. It's a distributed system, so it's fairly fast and it's performant, can handle loads of data. And with Amazon Elasticsearch, you actually make it a lot more simpler because you don't have to deal with the whole management hassle of the clusters, etc., because it takes care of that for you. And of course, if you have your data within AWS, let's say S3 or so on, it makes it much easier for you to integrate with it and get the data in and search on top of it. So let me stop there and hand over the stage to Phil, who's actually going to walk you through the MirrorWeb story. He's going to tell you about how they went about building the search architecture and what are the lessons and insights that they gained. Over to you, Phil.
Thanks, Chris. Right, so you've probably never heard of MirrorWeb, so I'll tell you a little bit about what we do. We provide web and social media archiving to public sectors and to regulated industries, so financial sector, FINRA regulated industries, and in the UK we've got similar regulations. But what we're going to talk about today is the public archive the web archive that we've done for the UK and national archives. And this is a publicly viewable archive available online. We also run the UK Parliament Web Archive, which is using similar technologies. But what we're going to talk about is the actual job we did to ingest all of the data for the UK Government Web Archive. So a quick rundown of what web archives are. I don't know if many of you are familiar with the Internet Archive and the Wayback Machine. Well, that's essentially what this is. Website data is stored in an ISO standard WARC format file, and it needs to be indexed to be covered and playback. I'm not going to go into details about what CDX indexing is, but the reason I need to talk about it is to explain how we did the indexing later. And so, what a CDX index is a list of all of the assets within the web archive, which would be HTML data, PDFs, and anything that was on that particular website. So we create an index, and that creates a text index of every asset in the file. So what is the UK Government Web Archive? Well, it's 20 years of historic archives. It's 120 terabytes of data. And we've got over 4,800 sites archived. A lot of these sites have been shut down and are no longer on the public web, but they're in our archive. We also archive UK government Twitter accounts and YouTube videos. So the UK Web Archive project, we won the tender last November to take this, to move this archive from its previous supplier, which was stored in data centers in Paris. And we needed to collect the data and move it into Amazon. Now, we were lucky that the data had already moved to the National Archives, but it was stored on 72 2-terabyte hard drives. And I had to go there with 2 snowballs and 2 machines that I built that we were able to connect 8 drives at once and ingest the data as fast as we possibly could onto the 2 snowballs, but it still took 2 weeks. The next phase of the project, we had to develop a public-facing website that was capable of serving over 75 million visitors a month. We had to provide full replay of all the archives, like the Wayback Machine, and then we had to do full-text search across the entire archive. The first 3 bits we were quite familiar with all of our financial clients, but we didn't provide at that time full-text search, and so we had a bit of learning to do. So, indexing 120 terabytes of web archives. We had the web archives are all stored in 100 megabyte files. So and they were all stored in S3. We had to filter down the content so that the search only provided results for government domains. Web crawlers traditionally kind of can spread off onto the internet and archive and pull down lots of stuff. We didn't want those returning in the search results. Only certain MIME types were in scope, so we only indexed text content, documents. We didn't index any video, we didn't index any images at this stage. The dataset also contained many, many duplicate pages, and we had a requirement that we were not to provide any duplicate results. So, choosing the search technology, there was two choices that we looked at that were popular at the time, Solr and Elasticsearch. Elasticsearch was the winner, as we've seen from the slides previously. It's very popular at the moment, but also Amazon offered us an Elasticsearch service. And we were a small team, and we didn't have a lot of search experience, so it made sense to have a look at running it on Amazon. We chose the Elasticsearch service for a number of reasons. Being able to scale was incredibly important. As you'll see later, we spun up a very large cluster to do the initial ingest and then scaled it back down to an affordable level when we went live. By using their service as well, it meant I didn't have to employ lots of Elasticsearch experts to run an Elasticsearch cluster, which did help. Managing the access rights to Elasticsearch can be via IAM, and that's integrated into the Amazon environment nicely. And we monitor it with CloudWatch and provide alerting along with all of our other alerts. And finally, failed nodes are replaced automatically. I don't have to worry quite as much about it as I would if we were running it ourselves. So traditional tools for indexing, we've got Hadoop and Spark. Now there are a number of open source projects on the internet for indexing web archives, but none of them actually pushed into Elasticsearch. So we were forced to look at writing our own. And the benchmark was set by the British Library. They run the UK Web Archive, and the UK Web Archive is UK domains, but not the government ones. So they set a record just around the time we were writing our software of ingesting 10 million records per hour. So we set that as our benchmark. Now what I wanted to do with the ingest job was to take the data stored in S3, process it with EMR through a filter stage, then do an extract stage where we then extracted the full text search from the documents that were in scope, and then we pushed that into the Elasticsearch. We didn't have experience of Hadoop, so we hired a Hadoop contractor, and they quoted us for 1 to 2 weeks of work to move this data into Elasticsearch. However, 2 weeks later, they told us it's going to take 6 to 8 weeks. Why is this? And it turned out we didn't realize that while Hadoop is great for batch data processing on small amounts of large files, this is the small file problem. We had 1.2 million 100 megabyte files, and not only that, they were gzip chunks files. So we had to move the whole data set from S3 into the HDFS to process it. We couldn't read directly from S3, just through the nature of each file had to be uncompressed. And with a WARC, we only want certain parts of it to be extracted. We don't need the whole file if we filtered it down. So we decided to think outside the box, and some smart members of our dev team came up with what we call WARPipe, which was, in a way, a rewrite of Hadoop for the cloud. So what is WARPipe? What did it allow us to do? It allowed us to run incredibly quickly and do the ingest at speeds that are unheard of. Each worker in WARPipe was able to access the data directly from S3 for the filter stage, and then was able to, we didn't have to move the data, so each worker had direct access to S3, and we were able to go, and we were able to scale the cluster on the fly as well. So what do we actually do with WARPipe? The data was stored in S3. We used 350 Amazon EC2 instances to do the filtering stage, and we were able to filter the files without reading the actual the WARCs. We did it with the CDX files. The CDX files contained a list of everything, every asset in the file. It just didn't contain the actual full text data. So we knew the MIME type, we knew the location, so we filtered down on the CDX files. Then the next stage, we had 650 Amazon EC2 spot instances that were doing the extract, and they could then take a chunk of the actual WARC data directly from S3 without us having to move the whole file. And then we pushed into Amazon Elasticsearch. Running that many boxes, though, did present some difficulties, and we managed to kill Elasticsearch many times until we got the scale right. So how do we optimize it? I ran a 9-node ES cluster with R4 4x large instances, giving us 144 cores across the cluster. I set the sharding to be 1 shard per CPU. To be honest, it was a bit of a guess, and it worked. But the first few times, we took it out when we had smaller and we had less shards. I had no replica shards for the ingest, because that slows things down. And then we used the bulk ingest API of our Elasticsearch to chunk the data in. I think we chunked it in at 2 meg chunks. So once the extract workers got up to 2 megs, we pushed that into Elasticsearch. So what was the result? It was fast, very, very fast. We managed to index 1.4 billion documents in 10 hours. And that was averaging 146 million documents an hour. It actually went quicker at times, but that was the average over the length of the time that we did it. And that meant that we didn't have to spend too much on the EC2 instances, and the Elasticsearch cluster that was quite large wasn't too expensive because we only ran it for the 10 hours. We also had this requirement to deduplicate, and we achieved deduplication by creating the Elasticsearch ID as an MD5 char of this string here, which every single asset in a WARC file has an MD5 digest generated, but it doesn't include the URL. So you might have a document that's in many different locations on different URLs, but it'll still have the same digest. So we created a unique digest and set that as the Elasticsearch ID. And what we did is we actually did push 1.4 billion documents into Elasticsearch, but we overwrote them. It was a very quick and crude way that actually worked very efficiently. So we indexed 1.4 billion documents, and then with this deduplication, we ended up with 333 million unique documents in Elasticsearch. It worked quite well. So this had an effect of reducing the index size from an expected about 8 terabytes. We inherited the previous supplier's index, and that was 8 terabytes, albeit that was in Lucene. And we got it down to 2.9 terabytes. And that's quite important because running such a large Elasticsearch cluster, the costs do go up as you add. You have to, I think the maximum drive size that we could get was 1.5 terabytes. So our current cluster is running 1.5 terabytes per node. So running at 144 shards wasn't something I wanted to do in production, and so we actually used the ES shrink index API to reduce the shards down from 144 down to 12. And that creates a copy of the index with the smaller shards, and then you remove the old one. And then we downgraded the cluster. This was one of the features of Amazon Elasticsearch. We were able to shrink the cluster down, and it managed it all down to 6 R4 X large instances. And then we have 3 M3 large master nodes. And then finally, we added a replica index to improve speed and redundancy. So what was the cost? Well, 10 hours of R4X large, 1,000 of them would have cost around $2,960. As it was, we didn't use 1,000 for the entire time because once the filter stage had completed, we were able to shut those down. But I ended up with a spot purchase price of $187. Phenomenal reduction. And then the large Elasticsearch cluster that we ran, looking back through our bill, we used it for 136 hours, and that cost us $237, which all in all was pretty cheap. So what did we learn? Well, I learned you can take down Elasticsearch very easily with 1,000 servers hitting it. And I think we'd 3 attempts before we got it right. And obviously tuning the index for indexing is really important. And one interesting thing you might not have realized, there is a 40 terabyte limit on EBS volumes. And we were running quite large volumes on all of these nodes, and we couldn't work out why we were booting up all these spot purchases. They were arriving on they were showing us booting up and then immediately closing down again, and it turned out that we'd hit this limit. So that's, if you're ever doing anything at that scale, make sure you get your Amazon limits increased. And then, yeah, spot purchasing can save loads of money. So, concluding statistics, what did we end up with? We ended up with 93% faster than the UK Web Archive's Hadoop cluster. Obviously, we've got a 70% reduction in cost with the use of spot purchases and 60% reduction in the index size due to deduplication. And that saved us a lot of money, that deduplication. Because if we'd had to run an 8 terabyte cluster with undeduplicated, it would have been very expensive. So I think I've gone a bit fast there. I do apologize, it's my first reinvent, but I'm sure we can do some Q&A.
Yep, sure. So, well, thanks, Phil. I think last bit, some closing thoughts. So as you've seen, there's a lot of flexibility that Elasticsearch offers, and Phil has already shared some cool insights in terms of how he has optimized it, especially with spot instances and how he's handled ingestion of smarter way, and also with Elasticsearch, how he gained a lot of new insights as he actually went about doing it, especially with shrinking the indexes and actually saving money on that. Hopefully this session was super enriching to all of you, and I think we'll be around here anyway for Q&A. So stick around, if we can actually take all the questions offline, more than happy to answer them for you. Thank you so much.
Thank you.